In this section, we're going to talk about related rates. We've seen that for quantities that are changing over time, the rates at which these quantities change are given by a derivative. If two related quantities are changing over time, the rates at which the quantities change are related. For example, if a balloon is being filled with air, both the radius of the balloon and the volume of the balloon are increasing as you're blowing air in. In this section, we consider several problems in which two or more related quantities are changing, and we study how to determine the relationships between the rates of change of these quantities. Before we get started, we want to review some formulas. So these are helpful formulas that you will need to remember. We have volume, surface area of a sphere, of a cylinder, of a cone, and then other helpful formulas, the area, circumference, and diameter of a circle, Pythagorean theorem, just some basic right triangle trig, rectangles, squares, cubes, and rectangular prisms. So I really recommend as you guys are going through problems, have this maybe like little page out for these helpful formulas if you forget what the formulas are. Okay, so related rates. Now that we're solving related rates problems, it's crucial not to substitute in known values too soon. So for example, if the value of a changing quantity is substituted into an equation before both sides of the equations are differentiated, then that quantity is going to behave as a constant and its derivative will not appear in the new equation that we find in step 4 that we're going to talk about in a minute. So if you think about this balloon, as I'm blowing in air, the radius is changing and the volume is changing as I blow in air. If I just said, oh, the radius is 5, well, that volume isn't going to be changing at that point because that means I'm no longer blowing that air in. So that's why we want to make sure that we don't plug in any specific known values until the end, and we'll go through that in this next example so you can kind of see a little bit more of what I mean. So here is the problem-solving strategy that I recommend for going through and doing related rates problems. The first is to draw a picture, if possible, that represents the situation. I know that for me, if I can visually see what's going on, it's super helpful. Assign any variables to any variable quantity and make sure that you remember those units. State the known and the unknown rates using proper derivative names and including units. Write an equation that relates the two quantities, and then you're going to relate the rates using implicit differentiation on the equation that you found in step 4, and then you'll substitute the known rates that you know of to find the unknown rate. That sounds like a lot, doesn't it? So take a deep breath and let's start working through some problems. Let's look at this example. A spherical balloon is being filled with air at the constant rate of 2 centimeters cubed per second. How fast is the radius increasing when the radius is 3 centimeters? So we're not wanting to know what is the radius when the radius is 3 centimeters because we already know that. We're wanting to know if you think about blowing in a balloon, that radius is going to get bigger and bigger as the time progresses. So let's go through our steps. Let's draw a picture. If I drew a picture, balloon's kind of like a sphere. We've got our radius. And obviously this is going to be getting bigger. So like as more time goes by, we'd have another radius that's going to be bigger than this radius that I have in this image. So I just want to make sure we know that. So this balloon is starting out small, then it's getting bigger and then bigger. So it's changing with respect to time as the more air is filled in. Okay, so we've done that. So now let's assign some variables, including units. So we do know if this is talking about 2 centimeters cubed per second, that's our rate of change for the volume. So let's let V equal the volume, because volume is how much air is in there. So obviously if they're telling us every second 2 centimeters cubed is getting in there, we know we're going to be dealing with volume. So volume is in terms of centimeters cubed. And then our other one, let's let R equal the radius, and that's in terms of centimeters. All right, so I've got step 2. Step 3 is talking about rates. So we're going to have the rate of the volume with respect to time, because the more time that goes on, that volume is going to change. And we have the rate of the radius is changing with respect to time. So we know that the volume is changing at a constant rate. So no matter what time it is, that volume is still going to be 2 centimeters cubed per second. I don't know what the derivative of the rate or derivative that the radius is changing with respect to time. That's what I'm solving for. But I do know this is going to be radius is in terms of centimeters, so it's centimeters per second. Okay, so step 4, find an equation that relates these two quantities. Well, luckily, we know a formula for volume. Volume equals 4/3 pi r cubed. Relate the rates using the implicit differentiation on the equation found to relate the quantities. Okay, so our whole goal is to find, we're trying to solve for this rate. The only way I'm going to be able to get that rate is if I take the derivatives of both sides. So the derivative with respect to time of v equals the derivative with respect to time of this whole side. So now I've taken this formula and I've turned it into relating it with rates. Okay, so let's find these. So this is obviously still dv dt. So that's going to equal, let's see, so 4/3, we can pull that out, and pi, because those are both numbers. So now I'm finding the derivative of the radius. So the derivative of the radius, so remember, this is a function with respect to time. Okay, we're finding the derivative with respect to t. So this is when we're going to have to do the chain rule again, just like we did when we were doing logarithmic differentiation and implicit differentiation. When we do this, we have to remember that this is a function of time. So when I find that derivative, it's the derivative of the outside, which is 3r squared, times the derivative of the inside function, which is just going to be the derivative of r with respect to time. And again, we're having to do that because we're not taking the derivative with respect to r, we're taking the derivative with respect to t. So when I simplify this, those are going to be gone, and we're left with dv over dt equals 4 pi r squared times dr dt. So our goal is to solve for dr dt. That's what we want to solve for. We know values, we know dv dt, and I also know I'm trying to find this when our radius is 3. Now again, notice I didn't substitute in the 3 here because this is, when we're talking about rates, we're not talking about at exactly 3, we're talking about as we're approaching. So you want to wait, that's why I said on that second slide, you want to wait until we get to the end to plug in these specific values. So now that I'm here, we can do that. So we know that the derivative of the volume with respect to time, I have that value, it's 2. And then I have 4 pi, and I'm solving for r, or I'm trying to find dr dt when that radius is 3. So that's going to give us dr over dt equals 2 over 4 times 9 is 36, so 2 over 36 pi. That's going to end up giving us, so that rounds to about, or that we'll keep it exact. So that's going to be 1 over 18 pi, and let's make sure we include our units, so centimeters per second. So when the radius is 3 centimeters, the radius is increasing at a rate of 1 over 18 pi centimeters per second. A 10-foot ladder is leaning against a wall. If the top of the ladder slides down the wall at a rate of 2 feet per second, how fast is the bottom moving along the ground when the bottom of the ladder is 5 feet from the wall? First, let's create a picture. So here's our wall, here's the ground. I'll draw my ladder. You guys can tell I have super great drawing skills. I wish I was good at drawing. It's the one class I got a B in high school. Okay, so let's look at what we know and let's assign some variables to some things. So we know this ladder is 10 feet long. Let's let x equal the height from the ground to the top of the ladder. So height from ground to the top of the ladder. And then that's in terms of feet. And then let's let y equal the length. I can't spell to save my life today. The length from the bottom of the ladder to the wall. And that's also in terms of feet. Okay, so if we think about this, before I even start plugging in values, let's think about it. I like to always try to visualize a picture. So if this ladder is sliding down the wall, this is going down, and this is going to be moving over. So let's think about what our what the sign should be for our rates. So here, the length of x is going down. It's going to be decreasing. So when I say dx, the derivative of x with respect to time, as time goes on, that rate, even though they told me it was 2 feet per second, but it is sliding down. So remember that rates also include direction. So that's really important that we think about that. Okay, and then we don't know the rate of change for that's happening when the bottom of the ladder is 5 feet from the wall. So that's what I'm solving for. So we don't know this, and again, that unit's going to be feet per second. And they told us we're wanting to find this when our y value is 5 feet. We'll use that later, so we don't want to put that in now. Okay, so we've done steps 1, 2, and 3. So now step 4, let's go through and find a relationship, a way that we can find an equation that'll relate all 3 of these together. So we've got x squared plus y squared equals 10 squared. We're using that Pythagorean identity. So x squared plus y squared equals 100. So now I have a formula that relates these two variables together. To get it so that I've got these rates in that formula, we'll do implicit differentiation. So we're going to differentiate both sides with respect to time, because again, these are changing, these values change as the time changes. So as more time goes on, the more that ladder has fallen. Okay, so again, remember, we're doing this with respect to t, and these are not t's. These are functions of t, because that x is going to change as the time goes on, and same with the y. So we're going to have to use the chain rule when I find those derivatives. So the derivative with respect to time of x squared is going to be 2x times the derivative of x with respect to time, using that chain rule. Next one is going to be 2y times the derivative with respect to y, or derivative of y with respect to x, and then that's going to be 0. So now what I have is I have a formula that has this dy dt that I'm trying to solve for. However, it has other variables in there, so I need to be able to find values for each of these variables that I can plug in. So let's see, we know that the y value is 5, so that's great. So I'm going to just rewrite this up here. So I know the y value is 5, but I don't know, and I know I need to keep dy dt in there. Let's see what else I know. Okay, well, I know dx dt, I know that's -2, so that's great. But how can I figure out what x is? I need a value for x. So let's go back to this original formula I had. We know this relationship, x squared plus y squared equals 100. Well, I'm finding this right when our y value is 5, so we can find the exact value of the x value. Oops, 25, I'm thinking ahead of the game. So x squared plus 25 equals 100. X squared equals 75. Take the square root of both sides. We get the square root of 75, which simplifies into 5 root 3. Okay, so now I have that value for x that I can substitute in. So again, our whole goal is once you get it to this point, you need to be able to use everything that we have to be able to find exact values to plug in or substitute in for all the variables that we're not solving for. All right, so when I do that, I end up getting negative 20 root 3 plus 10 dy dx equals 0. So 10 dy dx equals positive 20 root 3. So dy dx equals 2 root 3. And let's put our units in, that's feet per second. So we would write, to end this, we would say that the bottom of the ladder is moving along the ground at a rate of 2 root 3 feet per second when the ladder is 5 centimeters from the wall.